Good morning or good afternoon, everybody, depending where you are in the world. My name is indeed Olivier Felix, and I'm part of the Polyelectrolyte Complex and Material team, which is called PECMAT, at the Institut Charles Sadron in Strasbourg, which is in the northwest part of France. And in the next, before to start my talk, I would like to thank the organizers for giving me the opportunity to present some of our work. And in the next 20 minutes, I would like to show you how we were inspired by nature to prepare nanocomposite material with anisotropic properties. Through evolution, nature has developed nanocomposite material with complex structures and outstanding properties simply by combining strong and soft building blocks by a molecular assembly. On this slide, you can see two examples. The first one is nacre, that is composed of clay platelets and biopolymers that are assembled in a brick and mortar microstructures. And this composition and organization give, of course, the mechanical properties of the nacre. The second example is wood that has a hierarchical structures based on the assembly of cellulose at different length scale to form the tree. And again, of course, the composition and the organization of this cellulose gives the nice properties to wood. If you look a little bit closer to the wood cell wall, you will see that it is composed of different layers, a primary wall and a secondary wall, where the cellulose fibrils are oriented in different directions. You see random, unidirectional alignment, helical, and so on. And this, of course, gives the property to wood to be an anisotropic materials, as you can see here on the top. And you will notice that wood has different mechanical property depending if you are looking in the direction of the fibers, that means parallel to the grain, or perpendicular to the grain. That means wood is stronger in the direction of the fibril than perpendicular to them, as it is reported in this HB plot. And these, of course, properties have inspired the researcher to prepare nanocomposite materials with very good performance. Surprisingly, helical structures, which is probably one of the most complicated structures to assemble, is widely used in nature, in the plant and animal kingdoms, for preparing materials with outstanding properties. For example, in animal kingdoms and in the plant kingdoms, for example, damage resistance or structural colors. This brings me to, I would say, our goals by two questions. The first one is, can we assemble such complex nanocomposite materials? And starting from one anisotropic nanoparticles and one soft polymers, using an assembly method and to get such, to control the structure, could be unidirectional, cross-ply, or helical structures. And the second question is, can we get similar properties than who's found in nature? Of course, for doing that, we need an assembly method. If you look in the literature, of course, you will find different methods that can be used to align 1D anisotropic nano object, for example, field-induced, template-induced, polymer stretching, and microfluidics. But if you look a little bit more closely, you will see that these methods are not applicable to prepare complex materials like the helical one on larger areas. But of course, it is possible to assemble more complex structures like the helical ones, for example, at the microscale. It is indeed possible to prepare helical laminates just by peeling up some slabs, microscopic slabs. This is possible, that have damage-resistant properties. At the microscale, you can also find different approaches that can be used to prepare such helical structures, but they are not applicable to prepare complex material, like the helical ones, on large areas with a nanometer precision. Most of them have a micrometer precision. Or they cannot, I would say it's difficult for them to vary the composition. That's the reason why we use the layer-by-layer technique, and the principle of this technique is just reported here. It's simple, You just alternate oppositively charged molecules on the surface, and just by cycling this a certain number of times, you will build a lasagna. And of course, the property that you will design is based on the sequence and on the condition that you are using. Here you have three methods that can be used for doing LBL assembly. You have the dipping, that means you will just dip a substrate into a solution. The second one is spraying, that means you will spray the solution onto a receiving surfaces, and spin coating, it's just rotating substrate on which you will deposit, of course, drops of your solutions. The main advantage of this technique is that you can use a very wide variety of components that you can deposit or you can introduce into these multi-layer films, I would say. Can be nanoparticles, can be polymer, can be proteins, even cells. And another advantage is that you can play on a certain number of parameters to control the growth, the properties of your films that you will get. And one also important advantage of this technique is that you can introduce different properties in one single films. And this approach has been widely used in the world for preparing nanostructured films. And here you have only a few examples of application from this type of multi-layer structures. And today I will mainly focus on ultra-strong coatings based on cellulose. Okay, you have LBL assembly. We will start, as I said before, as nature, with anisotropic nanoparticle, that means a strong particle, and a soft one, which will be a polyelectrolyte. And the question is, does LBL assembly can be used to prepare such complex structures? That means unidirectional, helical ones, and so on. If you use spray or dipping, you will see that you will not be able to align your anisotropic nanoparticles. That means you will get a material where your anisotropic nanoparticle will be randomly distributed. If you're using spin-assisted assembly, that means spin coating, you will get alignment of your anisotropic nano object in one direction. That means you will get unidirectional alignment of your anisotropic object. And of course, if you want to build an helical structure, you will see that it's not possible to do it by simple LBL. That's the reason why we developed recently grazing incident spraying. That means instead of spraying your solution orthogonally with respect to the receiving surface, we will just spraying at a grazing incidence. That means with an angle lower than 20 degrees on the receiving surface, and you will get an alignment of your anisotropic object in the spray direction, simply like that. As you can see, for example, here you have a spray alignment using grazing incidence spraying in this direction. That means cellulose nanofibrils. Of course, you can measure the degree of orientation using an order parameter, which is called S2D. That means when this parameter is close to 0, it means that it's isotropic film. That means that you have no organization. That means your nanoparticles are randomly organized. If this parameter is close to 1, that means it's an anisotropic film, that you have a perfect alignment. Of course, in our case, it's very hard to get a perfect alignment, but you will see that we can get a S2D parameter close to 1. For example, in this case, it's 0.85. And this approach, that means GIS, grazing incidence spraying, can be extended to other types, of course, of anisotropic nanoparticles. Can be metallic nanoparticles like silver nanowires, gold nanorods, carbon nanotubes, and so on. But in our case, we will focus today on cellulose nanofibrils. Okay, that means now we have the hard, strong, and lightweight material, which will be cellulose nanofibrils. And you will get the soft matrix, which will be a polyelectrolyte. Of course, we can choose different types. I just put 2 examples here, chitosan, which is a natural one, and polyvinylamine, which is a synthetic polymer. And today I will focus only on polyvinylamine. And for this, we just combine these two types of components to get multi-layer nanoscale architecture, and you will try to control the composition and the orientation of the anisotropic nano object. And for this, of course, to build multi-property nanocomposite materials. Let's start with the random one. That means you start with dipping. That means if you combine the CNF, that means the cellulose nanofibrils, and the polyvinylamine, you can see that you can vary the pH. On this graph, you see the variation of the film thickness as a function of the number of layers and as a function of the pH of the polyvinylamine, because it's a weak polyelectrolyte. That means depending on the pH, you will change the degree of protonation. And you see that when you increase the pH from 8 to 11, you will increase the growth rate for your film. That means you will get thicker films at pH 11 than at pH 8. Using this approach, we can use a dipping robot and you can build a thick film. That, for example, here you have a film that is 1.6 micrometers. Then you can detach this film and you can see that you can get a transparent film that will be used later on to measure the mechanical properties by tensile strength. Now, if you want to build unidirectional films, we can use spin coating or spin-assisted assembly to get unidirectional films. And here you see the growth of the film. Again, it's the variation of the thickness as a function of the number of layer pairs. And you see that in this case, a linear or regular growth. And you see that your sample is changing colors. When you're increasing the number of layers, that means the refractive index is constant, but the thickness is increasing, and you are just going through the different colors of the rainbow. Now, if you want to check if your film is anisotropic, to just put it at a grazing incident, you can look with your eyes, and you will see different colors, which is characteristic of birefringence. You will see a Maltese cross, and this is due to the fact that the fibrils are oriented radially on the surfaces. If you look now by IFM, atomic force microscopy, at the center or at the edge of the sample, you will notice that at the center you have no specific orientation, that means you have different colors, but at the edges you will see an orientation of your cellulose nanofibrils in one direction as expected. What we can do now, we can also cut pieces of films in the direction of the sample, which is sample C, or perpendicular to the fibril, which is sample A, and compare it to the random one that was prepared previously, which will be sample B. And you can measure the mechanical properties of this film by tensile test. You have it here. That means you have the stress versus strain curve. And you can see that the best mechanical properties are obtained along the fibers. That means you have a value of around 500 megapascal, which correspond to medium quality steel for this film, which is only made of one polymer, and cellulose, which is also a polymer, but fibers in this case, only interacting with electrostatic interactions. The weakest is across the fibers, and in between you will find the random one, which is a mixture between these two. Now, if you compare this with other films that were prepared, nanostructure film that were prepared by LBL assembly, you will see that it's among the best film in this field. You can also compare this result with spruce, which is the tree from which the nanofibrils were extracted, and you can see that our film are stronger than the spruce from the wood where these nanoparticles were extracted. Now, if you want to go to more complex structures, for example, the helical ones, we first need to check how big is the area where these nanofibrils are aligned in the spread pattern. That is here. That's why we did an IFM mapping. And you can check the order parameters, which is on the left. And you can see that the best orientation is obtained in the red area. And on the right, if you look about the angle of alignment, again, the same zone, I would say, but it's in this case, it's not red, it's green. The other important parameter to verify, it's as we will rotate to make the helical structures, we need to verify that the layer that you want to deposit is not influenced by the orientation of the layer that is below. And that's what we did here. That means we spread films in two directions, parallel, or parallel and perpendicular. And in the picture shown in the middle, we have the first layer, which is top down, and the second layer, which is right left. And you can also measure the S parameter, that means the order parameter of each layer. And you see that there's now influence of the underneath layer for the deposited one. Now you can try to make now the helical structure simply by rotating the substrate by a certain angle. And this will allow you to control also the pitch and the handedness. Can be right-handed or can be left-handed. And you can also vary the number of layers that you can spray in one direction. But what you should notice also is that if you look at the variation of the film thickness as a function of the number of layer pairs, if you build a randomly oriented, an unidirectionally oriented, or a helically oriented film, you will not see a difference in thickness. Here you have just an example. You have the uniaxial one. Here you have just a code. The code is 97 corresponds to the number of layers. R1, that means it's a rotation right after the deposition of each layer of cellulose. Here it's after 3. You are rotating after 3 layers of cellulose. And here you have just the angle by which the sample was rotated, 15 degrees or 45 degrees. And you notice that you get the same linear increase of the film thickness as a function of the layer pairs. And here you have just two examples. You have, on the left, you have a left-handed helix with 3 turns, 15 degrees between each CNF layers. And in this case, you have 73 layer pairs of CNF and polyvinylamine. On the right, you have 144 layer pairs. It's a right-handed helix. You have 2 turns, and you have only 5 degrees between each cellulose layers. And you see, of course, the formation of concentric colors, and it's a gradient, simpler gradient of different thicknesses that you can measure, of course. And this is only due to the spraying setup. As you are rotating, that means you need to have an overlapping of the different cones, and this give you the formation of the helical structures only in the middle. Now, if you want to visualize this twisting of the cellulose nanofibrils, you are thinking about to do, of course, cross-sectional SEM, that means scanning electron microscopy. But if you do that, you will not see the twisting of the cellulose nanofibrils because the resolution was too poor. Because the cellulose nanofibrils, the diameter of the cellulose nanofibril was very low. They are around, I would say, between 2 and 5 nanometers, which is too low for SEM. That means we use a trick. That means we just build on a randomly organized films 2 helices of 500 nanometers each, but one left and one right. And then you can measure it by SEM, cross-sectional SEM, and you will see 4 sub-layers, which approximately, I would say, 250 nanometers, which correspond to each half helices that is shown on the left. And this is due to the fact, because if you want, when you are breaking your film, you will break selectively where your helices arrive nicely. Okay, this is indirect proof of our helices. How can we prove it really? For this, we used an optical measurement, which is circular dichroism. That means you just, when you have a sample which is optically active, you will just put a beam, which is right circularly polarized light or left circularly polarized light. And if this sample is active, one of these two, that means the left or the right circular, will be absorbed. And just by measuring the difference between the absorption of the left and the right, you will get a CD signal. That means in the case where you have an isotropic material, that means no activity, you have 0 in this case. And in our case, in this case, we used an helices which is unidirectionally and helical. and randomly organized, made of 97 layers. That means, I would say, a thickness around 955 nanometers. And you can, of course, play with the pitches by varying the angle or the number of layers. On this graph, you will see a left and a right-handed helix. That means you have the left, which is the red one, and the blue one, which is the right one. And you see that it's a mirror. That means exactly the same curve, not exactly, very similar, I would say. And for the random one, you see that you have almost no signal. Then you can also vary the number of turns. And you can see that when you're increasing the number of turns, you are increasing the intensity of your CD signal. You can also vary the pitch size. That means when you're increasing the pitch size, you see a red shift of the maximum of your peak. That means going on the right. And if you plot this maximum as a function of the pitch, you will see that that the position of the CD peak is redshifted linearly with the pitch as predicted by the Bragg law. And from the slope, you can extract the refractive index, and this refractive index is in agreement with what we use for ellipsometry. This brings me to my conclusion. The takeaway message. That means I will try to respond to the two questions that I have addressed previously in my presentation. Can we control the assembly as nature does? I would say yes, but probably not as good as nature does, of course, because nature did it for millions of years. We are just trying to do for only tens or hundreds of years. We did it by combining layer by layer assembly and grazing incident spraying for building complex architectures. We got ultra strong, transparent, and biodegradable films. That means you get films that are multi-properties. You are able to tune the mechanical properties. For example, they are sensitive to humidity. Mechanical properties that we got are above most of LBL assembled films. And which is also interesting, we got mechanical properties that are above the original tree where the cellulose nanofibrils were extracted. And this brings me, just before to conclude, I would also thank all the people that were involved in this work, and also all the financial support or financing institution. And I would especially thank Rebecca Blel, Randy Mujica, and Rémi Mérandol, who did most of this work. And I would like to thank you for your attention.